Hi, my name is Brett Redner, and I, along with Jacob Fedor, Alexis Rule, Jackie Lau, and Sarah Turks, are here to present our ChE 470 Senior Design Project, Glycols from Sugar. Now, to go into some basic background information of the project, we are simply converting sorbitol, given at a fresh feed capacity, and turning it into glycols such as propylene glycol and glycerol as a side product. Now, some basic facts behind it are in the capacity in terms of fresh feed of sorbitol is 122,000 pounds per hour. Our location here is the Gulf Coast as far as where the site construction would be, and our goal startup date would be April of 2019. Now, to go into the ATROR, a little bit of economics. The ATROR is simply incalculable at this point at the rates that we're selling at as well as our costs. And then the NPV after 15 years is a shocking negative $1.2 billion after 15 years. So to go into our recommendation, this site would simply not be financially feasible at this time. The ATROR of incalculable as well as the NPV of negative $1.2 billion after 15 years makes this a horrible investment opportunity and should not be further pursued. To get this, to get our ATROR up to 15%, the required percentage, the product would need to be sold at $1.80, and the current market value is 63 cents. So nearly double the market value to get it, to get this site into financially feasible, or over double to get the site as financially feasible. So let's look into our cash flow a little bit. To give a little background, these numbers are actually cents per pound of propylene glycol used. So as you can see here, that the utility cost, it costs 95 cents per pound of propylene glycol produced. Fixed cost, one of the smallest ends, is about 4 cents, and raw materials is about 77 cents per pound of propylene glycol produced. So digging deeper into our utility cash flow, as you can see here, our nearly 51 cents per pound of propylene glycol used goes to hot oil. And then wastewater accumulates to about 18, almost 19% of every pound of propylene glycol used. And now, to drop these numbers, as well as there's various other utilities as shown. However, to get our NPV down, or I guess get it increased, and to get our ATROR up to the 15% that it's needed, these costs would need to come down. These cents per pound of propylene glycol used would need to drop, so the cost can drop, the product, our total will rise, and then thus increasing and making this site more feasible, more financially feasible, and to move further along.
As we can see from the graph, the price of glycerol always fluctuate. But if we foresee for the next 30 years, there's definitely a downward trend that reflects that even though the product glycerol we are selling, even though we have make it more, the price go down, that will not recover our loss. So for the next one is the price of propylene glycol, which is also another product. In this graph, it shows that there's a increasing trend in the price. That means that in the future, if the price go up, it may cover some of our loss. And third, the price of sorbitol. So the price of sorbitol has been pretty stable, and in the future, we are not very sure what it will affect the operation costs.
As was already explained, our plant is not making any money. However, I have still conducted sensitivity analysis on several different things. First of which being propylene glycol, which is the main product of our process. Now, when I plotted it against the ATROR, I found that in order to make it profitable, it has to be 168 cents per pound, which is far above the market value at 63 cents per pound. Now, in order to reach the target of 15% ATROR, I had to raise it to about 180 cents per pound, and as you can see from the chart, going even further continues to raise the ATROR. Now, that is not a very feasible option, as people can get it much cheaper from a different vendor. Now, the second sensitivity analysis I did was deleting column 1. As pointed out in the earlier slides, hot oil was the main utility cost. Now, the majority of that hot oil is coming from the reboiler in column 1 due to the separation of water. Now, if there was some sort of technology invented in the near future that was able to separate out the water from all the carbon chains without boiling it off, then this would be much more economic, as it would reduce the cost by about 49 cents per pound. And we'd be able to sell propylene glycol at only 120 cents and be able to come out even. Now, moving on to the other analyses. Now, these two sensitivity analyses are associated with the profit of our process. The first analysis is with the operating time. Now, the reason for this is because no process is perfect, no unit operation is perfect, and if something goes down, say a pump, say a column, there's going to be some downtime, some unexpected delays in the operation. And you want to know how much money you're still going to make or lose if you keep going. Now, because we are losing money pretty fast, the less time we're operating, the more money we make. I do not recommend this process. Now, the second analysis has to do with the price of sorbitol. As Jackie pointed out previously, the price of sorbitol has been reasonably constant over the past however many years. However, things can change. You never know what's going to happen. So it's a huge part of our process, as it's the carbon chain that's getting cracked into our products. Now, if the price of sorbitol goes up, then obviously our costs go up considerably, as you can tell by that chart, decreasing our profit into billions more than it was previously.
Now I'm here to talk to you further about the economics of our project. With our capital cost sitting at $175 million and our utility costing us around $225 million a year, this takes up over 50% of our overall costs incurred just to build our plant and operate it initially. Our raw materials and our OBL costs take up only 7 and 9% respectively of our overall costs incurred, while our waste takes up $187 million, which is 27% of our overall cost incurred. As you can see in the graph shown behind me is both the rising costs of our two main products, propylene and ethylene glycol. Both propylene and ethylene glycol have seen upward rising trends in the cost that we would be able to sell them for over the past 10 to 15 years. Over the past 10 to 15 years, propylene and ethylene glycol have both seen anywhere from a 10 to 20 cent increase in their price that they can be sold for. Currently, propylene glycol is sold for around 60 cents per pound, and ethylene glycol is sold for around 30 cents per pound. With the rising costs of both propylene and ethylene glycol, we would be able to sell them as our two main products to be able to lessen our marginal deficit. Behind me, you can see a pie chart of our profit versus our expenses. In the green is what we can sell as a team, which will amount to $71 million a year. Our raw materials cost, which is shown in the yellow, is around $47 million a year. It's good that our raw materials cost less than our product streams because we're able to sell them for a profit. But as we know, with all product streams, we also have waste streams. We have to incur the cost of our waste streams and include this in to see if we would make a profit. Because waste is so expensive to process at around $30 per pound, we have to spend $187 million a year just processing our waste streams alone. In a pound-to-pound ratio, we're actually producing more pounds of product than we are of waste, but our product doesn't sell for more money than it costs for us to waste, which is why we won't be able to make a profit just based on our waste cost alone. Now I'm going to talk to you about both the hard specs and soft specs we had to meet as a team for our project. Some of our hard specifications was that our product streams, which we showed you before we could sell for $71 million a year in profit, had to be of 99.5% purity for them to meet specifications for us to be able to sell. This is why we had to have 7 distillation columns in our whole process, was to meet the right purity for us to be able to sell our streams. Another hard specification that we had to meet, which Jackie will talk to you about later, is the handling of hazardous waste. A lot of our waste streams contain lactic acid and other harmful chemicals that are really dangerous to handle, so we had to be careful and put specifications into our process and our operating parameters of our plant for our operators to know how to handle these chemicals safely and not be harmed. Along with the hard specs of our projects that were absolute have to be met requirements, we also set some soft specifications for ourselves to meet as a team. Some of our soft specifications came in our distillation columns. We wanted to make all of our reflux ratios less than 10 to have our columns running at optimal conditions, as well as to have a height of less than 250 feet and a diameter of less than 16 feet, which would provide reasonable distillation columns that could actually further be built in the future. All of these specifications for our distillation columns were met. Some other soft specs that we had as a team were to minimize our capital and our waste costs. We actually did minimize our waste costs in using one of our waste streams we had originally had as waste, which we calculated out to be $1.4 billion to waste a year. And we determined that the stream is mostly water and we could use it for cooling utility throughout our plant. So this allowed us to both lower our utility and our waste cost, even though in the end our waste cost is still much higher than our overall profit will be. Another thing that we wanted to try and meet as a soft specification was to maximize the production of propylene glycol, because set out in our project statement, it was our main product to be produced. We were able to maximize the production of propylene glycol as we produced it in 3 of our 4 product streams that we were selling as a plant.
Next, I'm going to talk to you about the overall design of our plant. This shows a block flow diagram of the first half of our design. This starts out with inlet feed streams of sorbitol and water, hydrogen and methane, and sodium hydroxide and water. These feed streams will be fed into a dual reactor system that operates in parallel. This was designed this way so that we wouldn't have to shut down the plant while regenerating and replacing the catalyst. So one reactor will run at a time. The design for the reactor was chosen based off a patent design, and we chose a patent that converted sorbitol 100%. Now, we continue this design through our ion exchange as well. We have a dual ion exchange that runs in parallel for the same reasons. We're going to have to regenerate and replace the resins in each ion exchange, so only one will run at a time so we don't have to shut down the plant. This will then go into a hydrogen flash operating unit, which actually will recycle the hydrogen back into the system so we don't have to worry about another waste cost. The second half of our block flow diagram shows all of the distillation columns. We are actually selling propylene glycol and glycerol, and we are wasting 4 other streams from the columns. We have a total of 7 columns that all operate with the condition of 95% purity for all of the streams that we are selling. Next, I'm going to talk to you about an alternative case study that we did. So we have decided to add an extra distillation column after column 4. This will allow us to sell another product of 2,3-butane-diol. The capital cost of adding this column was roughly about $1 million, but we are able to sell our 2,3-BDO product for about $5 million a year. So the total capital cost will increase by $1 million, but the waste is going to decrease by about $10 million. This is because the waste stream that was originally coming out of column 4 was so great, and by adding this column, the waste stream out of column 8 is far less than it was in column 4. This design is beneficial for us to lower our waste cost, but it will increase our capital cost of about $1 million.
So right now I'm going to talk about the safety and environmental section. The idea of inherently safe design is introduced by Professor Kluss in the 70s. So there are 4 main ideas of this safety design. First is the substitution. So in our design, since sulfuric acid is going to be corrosive to carbon steel, we substitute the carbon steel into 3/16 stainless steel. So for the second idea, it will be called minimization, which we try to optimize the distillation columns. In gate 3, we have the reflux ratio at 50 and the number of stages at 100. But in gate 4, our team managed to optimize it to 10 and 40 respectively. So next I'm going to talk about modification. What that means is try to modify the process or the equipment to prevent the possibility of any hazard. So in our cases, under high pressure, we should not use gas because it's going to cause any kind of explosion. We should use cold liquid instead. Besides, we also want to optimize the temperature and pressure so that we want to use lower pressure, lower temperature to prevent hazard. Last but not least is the fourth, called simplification. In our project, if we want to get pure products, we can try to install more distillation columns. But under the idea of simplification, we should just try to find a better distillation method instead. So here's the timeline for the plant construction. So the planned start date will be in April 2019, and it takes about 3 years to construct the entire plant. As you can see that most of the time was spent on building the plant and also get the permit approved. So for some other time it will be to buy the equipment, to test the equipment, and also a bunch of safety things which add up to be about 3 years. To conclude, our group was managed to convert sorbitol into glycerol and P-glycol, which will be sold. However, the plant is still in deficit due to the high fixed costs, high operation costs, mainly on the waste treatment and the low production. So we suggest for the teams in the future to look into ways to lower the waste treatment costs by looking at more research to see if there's a way to reduce that. Finally, we would like to thank our mentors, Bryan and Amber, and also Professor McFadden for all the helps, and I would also like to thank my teammates for all their works.